Hey there guys, how you doing? This is another Parker Screencast, and today our goals are going to be looking at some different forms of mechanical energy, specifically kinetic energy and potential energy, and how is it that those formulas came to be. And if we have time, we'll look at power. So kinetic energy. Let's consider trying to get an object moving. Remember that our formula for work is force times distance. But what is the energy required to get the object moving? We can start doing substitutions. We can, instead of F, we can put in MA. So work makes you mad. Ha ha ha. Well, anyway, we're going to keep going with the substitutions. We're going to solve one of the kinematic equations for A. So that v squared equals v0 squared plus 2ad. We're going to subtract v0 squared from both sides. Switch the order and divide both sides by 2d. So we have this equation here that we can then substitute for a. So instead of a, we have this big whole mess right here. Now, one of the nice things is the d's cancel out, the distances cancel out, and we're left, and then we're going to distribute the 1/2 and the m. So we end up with this work is equal to 1/2 mv squared minus 1/2 mv0 squared. This is where the concept of kinetic energy comes from. Kinetic energy is 1/2 mv squared. It comes from this definition of work, substituting instead of a, looking at what are the velocities. So here's our first definition. Kinetic energy is equal to 1/2 mv squared. And we have the familiar units of the joule for this this formula, or for this concept, which is composed of kilograms per meter squared over seconds squared. Let's do a quick calculation. What's the kinetic energy of a car driving down Clabbered Ridge Road? We list out our variables, we get our formula, we do the work, and we end up with a kinetic energy of about 100,000 joules for a car doing 12 meters per second, which is somewhere around 27 miles per hour. What if we doubled the speed of the car? So going down the highway, like 55 miles an hour. What happens to the kinetic energy? If we plug those numbers in, we get 400,000 joules. So we double the speed, but it quadruples the kinetic energy. We have this squared relationship between velocity and kinetic energy, where a small increase in velocity gives us a much larger increase in kinetic energy. Let's go back to that work formula that we had. Work will cause, if you put, remember work is a transfer of energy. If you do work on an object, one thing you could do is change its velocity. This is called the work energy theorem. Doing work will change an object's kinetic energy. So if you want to go from 40 miles an hour to 80 miles per hour, you have to put a lot more energy into an object. 4 times as much energy to double that speed. The inverse would be true. If you wanted to go from a very high speed to 0, the best way to do that would be to put the brakes on in your car. That means you have to take away all that kinetic energy, or all that energy of motion, away from the car. That ends up taking a lot of work to change that kinetic energy. And in this case, if you're going from a positive velocity to 0 velocity, you would actually end up doing negative work. This is why traveling at high rates of speed requires a much larger stopping distance. If you're going double the speed, it doesn't just double the stopping distance, it actually quadruples the distance it takes to stop. Now let's take a look at potential energy. Since work is a transfer of energy, we can end up doing the same kind of thing where we do some substitutions. Work is equal to force times distance. If we are looking at lifting something against the force of gravity, we can look at F sub g, or Fg, multiplied by distance. This would, remember, Fg is really mg. When we're talking about lifting something against the force of gravity, instead of distance, we would use the concept of height. So this is where the definition of gravitational potential energy comes from. Again, it comes from our definition of work. And of course, we have the same units for potential energy. Whether we're talking about work, a transfer of energy, potential energy, or kinetic energy, it's all measured in the SI unit of joule. The thing you got to be careful of is you need to specify where is your zero line. If I'm lifting something against the force of gravity, where do I call that zero? So where would my potential energy be zero? For instance, if you were hiking Mount Washington, I've hiked Mount Washington a few times in my younger days, and I started somewhere down here, hiked up Tuckerman's Ravine. What if we wanted to see what is the change in kinetic energy or potential energy of a 90 kilogram hiker going from Tuckerman's Ravine all the way up to the peak of Mount Washington? It's an amazing hike. You can do it in about a day. Of course, I wouldn't do it in the winter time. But let's take a look. 90 kilograms, acceleration due to gravity 9.8. Our height, in this case, is 2,547 feet, which is 776 meters. So our potential energy, mgh, is those three quantities multiplied together, giving us a potential energy change of 690,000 joules. Now that's from calling Tuckerman's Ravine the 0 point. If that's 0 and then it's 690,000 joules to get from Tuckerman's Ravine to the very peak. What if we were to go from the peak all the way down to sea level? Now we're going to call sea level our 0. So mass g, this time hiking down, it's a negative quantity. Our height is going from the peak down to sea level, which is negative 1,922 meters. We multiply those quantities together and you have a negative potential energy change of 1.7 million joules. So again, on potential energy, it's important to indicate what would our zero level be. For instance, if you're in my classroom and you lift up a book off the table, are you calling table the 0? So you're measuring from the table to the height that you lifted to, or are you calling the floor 0, which would be an increase, or are you going to call the ground 0, which is well below the floor relative to my classroom? Hiking is fun. I've never taken the Cog Railroad. There is a train that actually goes up Mount Washington. It's a world famous train. It's a Cog Railroad. The reason it has the name Cog is because the track is so steep that the wheels actually have little cogs that fit into grooves on the track. It's also famous because the boiler itself of the steam engine tilts so that the boiler is always level. Someday I will ride the Cog Road. Can't wait to give it a shot. So that's it for kinetic energy and potential energy. That should give you enough information to be able to complete the next few pages of the packet. Things like, can kinetic energy ever be negative? Well, remember the velocity squared, and you can never have negative mass. And then some relationships between energy and velocity. Also, I'm working on the assumption you may not have a ruler at home, in which case I have put in these measurements here. We're going to pretend that it's scaled. So that's half a meter, it's 2.3 meters, and that's 4.2 meters. And I'm measuring, assuming that this is the 0 line right here. Now let's take a look at power. Power is the rate at which energy is transferred. So work is a transfer of energy. Power is how quickly you transfer that energy. When you think of, or when you hear the word power, a lot of different things might come to mind. But in physics, just like work, power is a very specific meaning. So work is a transfer of energy. Power is how quickly or how much time it takes you to transfer that energy. The SI unit is joule per second, which gets a special name called the watt, named after James Watt, who was a perfecter of the steam engine. Let's do a quick calculation. A car engine applies 20,000 newtons for 100 meters in a time of 20 seconds. How much work did it do? So I list out my variables. My formula for work is FD, so I have 2 million joules. What about the power? What is the power applied by the engine? Well, the variables are listed here. The formula, this time I have to use the formula for power. I do my work, and I end up with a power of 100,000 watts. So applying this much force over a distance of 100 meters in 20 seconds gives you 100,000 watts. In Europe, actually most countries, this is how they measure the power of a car. They say that the engine has a 100,000 watt engine or a 100 kilowatt engine. So you would, Toyota Prius would be a car that would have about a 100 kilowatt engine. Of course, you could go to something a little bit nicer like a Ferrari, which has a 360 kilowatt engine. That is measured in a slightly more familiar term of horsepower. Horsepower is a measure of power, but this is an English measure, whereas the watts is the standard SI unit measure. But all that to say, if you wanted to go from 0 to 60 in less time, if you want T to be smaller, P will have to be bigger. The power of your engine would have to be bigger in order to have a shorter time for that energy transfer. The conversion between horsepower and watts is here. 1 horsepower is equal to 746 watts. And the horsepower originally came from James Watt. The first steam engines, one of the jobs that it was doing was removing water from a mine, pumping water up and out of a mine. And he decided that a good way to market this would be to compare how his steam engine did against the effort that a horse would have to put in. In other words, they were using horses to pump water out of a mine, and he used a steam engine to pump water out of the mine, and he was showing that his steam engine was the equivalent of however many horses doing the same amount of work. But again, that's where the concept of the horsepower came from. Alright, let's do a quick power calculation. With this power calculation, we'll call this video over. Let's say you want to eat a quarter pounder with cheese. Here are the formulas that you're going to end up using. And we're going to do some estimates, like the mass of a quarter pounder is about 0.1 kilogram. The distance you would have to lift it would be about 0.5 meters. Take you about, say, 1 second to lift that hamburger up. And acceleration due to gravity is 9.8, of course. We're going to end up using all those formulas to do this calculation. Now we do the work. The weight is 0.98 newtons, so the work done is 0.5 joules. And if you did that in a time of 1 second, you did about half a watt of work lifting that quarter pounder with the cheese. And that's really all there is to it. You end up doing multiple steps to get to that final result, but it's just a logical progression of one formula to the next. And that's going to do it for this screencast. So at this point, you now have enough information to do most of this worksheet. You should be able to do through the power sheet. When you get to the conservation of energy, stop. And also use the online textbook as a resource. There is a tremendous amount of information listed within the online textbook. Well, enjoy your weekend. We'll see you on Monday.